Hi everyone, how's it going? We're going to continue where we left off, basically with the example of the net change theorem, where we were looking how it relates to applications to velocity, displacement, and distance. So remember, we said that the difference between distance and displacement. Okay, distance takes every movement as a positive number. So normally, if you are moving, let's say just in one dimension, moving to the right is a positive displacement. This is by convention, you know. We could have made this negative if we wanted to, but it's just a way that by convention we're used to this. So and like positive. So right is positive. And moving to the left was negative displacement. So for example, if I went if I went, and let me face this way so it's the same. If I go one step to the right and then one step to the left, I've essentially displaced 0 steps because I went one step right, one step to the left, so that's like 1 plus -1, so a net of 0. But in terms of distance, I traveled 2 steps. Distance doesn't care whether you're going right to the left. It's going to count that as distance. And so because of that, and the net change theorem, we know this. We know that if v of t, this quantity here represents the velocity of some particle or some person or some object as a function of time, this is going to be total displacement from time t1 to t2. So this will give you the displacement. Remember, the net change theorem gives you the net, so maybe net is better as opposed to total. So net displacement from time t1 to t2. And then if we take the absolute value of this now, meaning that we count motion to the right as positive velocity and motion to the left as positive velocity, doesn't matter. This will give you, take down the absolute value, difference here, this is net distance traveled. Okay, so that's the net distance. So note the absolute value is there to make things going to the left positive, essentially. But in displacement, we don't want to do that. We want to keep positive and negative things separated. Okay, so now with this, we can look at an example, another example of the net change theorem, which is essentially just a fundamental theorem of calculus. It doesn't really, it has a different name because it has more physical meaning than just the bare fundamental theorem of calculus the way it's presented. And by fundamental theorem of calculus, I mean both parts, 1 and 2 together. So just in general, that one. So here's an example. Say we have a particle moves along a line. So So we have a particle, it's moving in a straight line, so it could go right or left basically. And its velocity at any given time is given by this function, t squared minus t minus 6. And we're going to measure this in meters per second. And yes, so let me write that in meters per second, okay? So there's two parts to this question. We want to know what is the displacement on the interval 1 to 4, okay? So from 1 second into its motion to up to 4 seconds, how much has it displaced? Okay, and like we talked about earlier, the answer to this is just going to be the integral. This is like t1, this is like t2, so it's going to go from t1 to t2 of the velocity function, just like that. So here we didn't need to take any absolute values and worry about that. This is the nicer case, okay? And then again, because of the properties of the integral, we can break this guy up to 3 pieces. So we have 1 to 4 t squared, and then minus 1 to 4 t. Oh. If you guys were alive in class, you should yell at me for this. I forgot to write dt here, so we want to not get into a bad habit. So I wish you guys could yell at me in real time, but I'll have to try and yell at myself at this point. Okay, and this just follows simply by the properties of the integral that we talked about. Okay. Now, if you use the power rule here, this integral is 1/3 t cubed, and this is evaluated from 1 to 4. Remember, we read this evaluated from 1 to 4. And then this guy is 1/2 t squared from 1 to 4, and then minus. And remember, if we had a constant, all that would happen is we would get that constant times this variable, so 6t. Had it been an x, it would be 6x. So then we get 6t. That followed again by the power rule, but it's a little lengthy to discuss it again. So we have this. Okay. And then let me erase this so we can do our calculation. So again, what did this mean? This means you're going to stick 4 into this function, so 1/3 4 cubed, and subtract that from what you get when you stick 1 into this function, minus 1/3 1 cubed, okay? And that's all this chunk. So this, all of this expands into that, okay? And then minus, now the same thing. And because this is a quantity, we want to put all of it in parentheses. So 1/2 2 squared, sorry, 4 squared, 1/2 4 squared minus 1/2 1 squared. Again, that's this piece. Look, so the minus has to hit the net result. So we have to do the algebra first and then hit it with the minus. Or if you want, you can distribute this minus sign right now and not worry about that. So it's just up to you, the choice which you do this. And then last but not least, minus 6 times, so again, parentheses, 6 times 4 minus 6 times 1. Okay? So this is all really important to do this all properly. Okay? Now this is one way to do it. We could do this. Another way is to kind of combine it all. At the end of the day, it's not going to matter really. So what I mean by that is we could have, the integral we found is that this integral was 1/3 t cubed minus 1/2 t squared minus 6t, we could have then evaluated all of this, the whole thing from 1 to 4. So we stick 4 into all of these initially, and then subtract it from what happens when we stick 1 into here. But you can see that if you do algebra, you're going to get the same thing. It's that and these are equivalent, but some people just at first maybe appreciate one way over the other, but you'll see quickly that they all give you the same thing. It doesn't matter too much. Okay, so then 4 cubed, 4 times 4 is 16, times 4 is going to give you 64, so we have 64 over 3 minus 1 over 3 here, okay? And then 64 over 3 minus 1 over 3 is just 63 over 3. Okay, so net we get 63 over 3 from this, minus, okay? And now we have 4 squared over 2, so let's just write that as 16. So minus here, 16 over 2, minus 1 squared, so 1 over 2, okay? So what does this net give me is 15 over 2, right? So I'm going to have a minus 15 over 2. And so you might have been tempted to be like, oh, well, 16 over 2 is 8, but then you're going to have to combine it with this fraction. So you would, again, have to just turn it into 16 over 2 again. So sometimes it's better to not simplify. It's kind of weird, but in this case it helps. And then minus, again, so 6 times 4 is 24. And then minus 6 here. So that's just going to be 18. So this is just minus 18. Overall. Okay? And now we essentially need a common denominator because this is like over 1. And the common denominator between all of these is going to end up being 6. So, at this point, once you do everything, do the algebra, at this point, this is just arithmetic, so I'll leave it up to you. You'll end up getting negative 9 over 2 meters. Okay, so that becomes the final answer. Okay, so, once the dust clears, you will have a denominator of 6, but then something's going to cancel with that so that you essentially get a 2 at the bottom. This is just arithmetic. So this ends up being the answer. The hard part is to see how to do the calculus. The arithmetic I leave to you. Okay? And then part B, it says find the distance traveled now. So find the distance okay, so now instead of finding the displacement, we want to find the distance traveled. And this is much harder because you have to deal with the absolute value of the velocity instead of just the velocity. So you have to figure out how to decode what this absolute value business means. So if you remember, the absolute value of any input x, so x can be anything. In math, x just is a placeholder for any combination of things. So this could be extremely complex. It could be like 4t squared minus 16t divided by the square root of 7. But you just write all of that as x. X is just something. It could be anything. It doesn't just have to be a single term. It could be a many-term thing. So the absolute value of x is defined this way. Which you probably have seen a lot from your Calc 1 class. So all it means is that at the end of the day, if your input, no matter how complicated it is, it doesn't just have to be one symbol. If it ends up being 0 or negative, you don't change it. If it is negative, though, you just tack on a minus sign into it, okay? So let's see what that means for our thing, because we're taking the absolute value of the velocity, right? to do this integral, we need to do this. So we're taking the absolute value of this function essentially. So this is like x. Remember I told you x can be many symbols, it doesn't just have to be one. So in this case is x. So whenever this entire expression is 0 or positive, we're just going to leave it. And anytime it's negative, we're just going to tack on a minus sign in front of all of it, in front of the entire quantity. So this is what I mean. So this literally means you leave the function the way it is if all of this, or you tack on a minus sign in front of all of it. So notice this minus sign distributes to all of this. Okay, so that's how we are interpreting the absolute value of v of t. Okay, so now your question may be, okay, how do we find when these conditions are satisfied? And the easiest way would probably be to just graph this guy. Okay, so you can find the x-intercepts of any function by setting it equal to 0, right? So if you set this thing equal to 0, this is now, you know, from algebra, you know that this thing factors into t minus 3 and t plus 2. And so you know that t equals -2 and 3 are x-intercepts, or roots as you would say, of this guy. So that's one piece of information that we're going to use. And the other thing is, we know that this is a very special kind of function. It's a polynomial where the degree is 2. These are called quadratic functions. Fancy name. And because this t squared is positive, it's not like a -t squared or -2t squared. We know that it opens up. So we essentially know that the graph looks like this at this point, because these are the x-intercepts and the thing opens up. If this is time and this is the velocity, we know that at -2 and at 3, or I should put these a little further away. There's 3. We know that the function is 0 at these points, and it opens up, right? So it can't go like this. It can't be arced like this, so it has to be arced down like that. So it looks something like this. That's what this function looks like. Okay? And so from here, you can very quickly see these conditions. This basically means the function touches the x-axis or is above it. So like in this scenario, this branch and this branch represent that. So from time 3 seconds and on, since we don't want to consider negative time, in some contexts you can, but we're only considering the interval from 1 to 4 anyways. So here's 1 to 4. So we're only looking at this chunk anyways. So these set of outputs, we're just looking at this branch, really, in our case. So this branch, we can see that the function satisfies this because its output, which is t squared minus t minus 6, is either 0 or positive. So we know this occurs, this is true when t is in the interval 3 to 4, from what we care about. You know, it's really 3 to infinity, but from what we care about, 3 to 4. And this occurs when t, now this means it's beneath the x-axis. Your output is negative, so in this branch. So this means that t is in the interval 1 to 3. And you might be like, okay, which one of these do you take? Because you're including 3 at each of these points. It really doesn't matter, so let's just do this. There's a very, very technical reason why you can just ignore a single point when you're doing an integral, but that goes very far into some deep, deep math, so just take my word for it, I guess, if you want. Okay, so with this established, we can now calculate the integral. So now we know that the distance traveled is the integral from 1 to 4 of the absolute value of this guy. Okay? Which, remember how we could break an integral up into an intermediate point? Like we said, if we have the integral from a to b, we can say it's from a to c, and then from c to b. You know, some intermediate point. C is a number between a and b. This property is exactly what we're going to use. So, because we know that this is true, we know that from 1 to 3, we have to put a minus sign in front of the function. And from 3 to 4, we don't need that minus sign. Okay, so then this is going to be the integral from 1 to 3. And then we need the minus sign here. And plus the integral now from 3 to 4. And then we don't need the minus sign here. Okay, so this guy breaks into that. And you can take this integral in a very, very similar way as to the way that we did in the previous example. Because once you do this small trick, you're done. So, right, this minus sign will distribute to each of these. So this really is the integral from 1 to 3 of negative t squared plus t plus 6. Oh, I did it again. I forgot the dt. The dt. And then plus 3 to 4. Okay. And then now we know how to do each of these. Again, we discussed how to do this essentially in the previous example, so I won't redo the arithmetic again. But as you can see, when the dust clears and everything like that, you get 61 over 6. So that's the distance traveled, as opposed to how much it's been displaced. And then this would be meters. Okay, so that's essentially just the net change theorem. And you know, this comes up a lot because many physical quantities in nature, like one is the derivative of the other. So anytime one quantity is the derivative of the other, net change theorem is going to come into play. So it's pretty important and powerful. Okay, at this point now, we can move on to the next section. So this whole time, we've kind of been taking integrals that are in a very, very nice form. And again, remember, I told you guys that integrals are more challenging in general than derivatives. So we're going to start to delve into some of the techniques of taking harder integrals. There are techniques. So a lot of this class is dedicated to learning these techniques. And a very, very important and useful one is called the U substitution or the substitution rule. So the substitution rule, okay? And so here's a motivating example for this. Okay, so let's say that we want to take this integral. Squared right now. Okay. So all of the techniques that we know up to this point won't let us do this, because if we want to split this guy apart, we needed like a plus in between here or something, or a minus or anything, you know, we've never dealt with the product of two things, first off. And second of all, we don't even know how to take this guy by itself, right? We have not discussed how to just take this one. Like, say we know how to take the integral of x squared, but how do you take the integral of, say, x plus 1 squared? That's a very valid question, right? And you may start to think, hey, this is kind of like the chain rule, because, right, we did this with the chain rule. I know how to take the derivative of x squared, but how do you take the derivative of x plus 1 squared? You needed the chain rule to do this. So this is kind of like a similar idea. Okay. So the idea is, and this technique is called substitution, or also, let me see, note. So substitution or U substitution. Very commonly called U substitution, which we will see why in a second. So the idea here is to let this variable U be something that we see here. So what we're going to do is we're going to say, how about we just let U be 1 plus x squared? And again, this seems very arbitrary, and in a sense it is, so you may be very questionable, like, what are you doing? But, you know, we see a 1 plus x squared in here, okay, and we let U be that. So then, if we take the, you can say maybe the derivative on both sides, if we turn this into a differential, so remember differentials like du and dx. So essentially just take the derivative of both sides. So just a u will turn into du. And maybe it's worth it to show this once in full detail so that you see what I'm talking about, and then we can not do this. So if you take the derivative with respect to x of both sides, then remember, u is a function of x. It depends on x. So in general, its derivative we can write as du divided by dx, right? Or divided by is kind of scary to say, but we're going to think of it that way. So this is du over dx. And then this just ends up being, you know, what's the derivative of 1 plus x squared? This is 0, and that's 2x. So this is 2x. And now you're going to multiply both sides by dx. So multiply by dx, multiply by dx. So it cancels here, and you get du is 2x dx. Okay? And so we'll see in the future that we won't do this whole process again. We'll just say, okay, take the derivative of both sides, and that'll give du is the derivative of this dx. So you'll see what I'm saying in a second. Okay? So this is important that we got this result. So du is 2x dx, okay? So what does that mean that dx is this guy here? Well, if you divide everything by 2x, divide by 2x on both sides, we get this final result that says that du divided by 2x is equal to dx. This right here. Okay, this is important. So now, if we want to substitute this integral, if we want to change its form, what are we doing? So this integral, its new form, will be the integral of 2x, and then we change this to u, right? 1 plus x squared is u. So the square root of u times, what did dx change to? Dx changed into du divided by 2x. And bingo, this is a really cool part. This 2x now cancels with that 2x. And so this kind of justifies the choice of the u, why we picked u to be this. So in a second, I'll show you why picking u to be 2x is not going to help us. So let's just work through this example, but it's very important that you pick the right u. Okay, so then these cancel, and then we're just left with this guy. The square root of u du. And this is perfect. We have a function with a u in it, and the variable is u. So we know how to take this integral very easily. Okay, let me come up here to do that. And remember, the square root of u you can write as u to the 1/2. Okay, and then we apply the power rule. So all this is remember, you're going to take 1/2 and add 1 to it. Let me leave some space. You take 1 over this guy plus 1 times u to the 1/2 plus 1. That's what the power rule says, plus c again. Because this is an indefinite integral. Okay, so 1/2 plus 1 is 3/2. So we have 1 over 3/2 times u to the 3/2. And then 1 over 3/2 is just 2/3. So this is 2/3 u to the 3/2 plus c. But, so this is an acceptable answer. This works. But what we could do is, if we want this in terms of the original variable x, what you do now is resubstitute in the x expression. So u, remember, u is equal to this, 1 plus x squared. So let's just make that replacement here. So we have 2/3, the whole u, which is 1 plus x squared. Because it's a quantity, you have to put it in parentheses. It's not just a single term like x or x to the 5th. You know, it's multiple terms. So you put it in parentheses, raised to the 3/2 plus c. And this is the answer. So this is how we can get it. This is a new technique that we have developed for being able to find integrals, and it's called u substitution. So let me talk about maybe why we had to make this choice of u, because it's really important. So let's write the original problem again. Okay. Yeah, say we did let u be the other thing. What if we let u be 2x? Okay. Now, if we take the derivative, remember the shorthand way is u will turn into du, and then you just take the derivative of this, which is 2, and then whenever you do that, you just tack on dx. So take the derivative as normal and then tack on dx. Okay, so then what do we get when you divide by 2 is that du divided by 2 is dx. So what would our integral look like? The new integral would be the integral of u square root of 1 plus x squared, right, that's u, times what dx was. Dx is replaced with du over 2. Now this doesn't cancel the same way this one did. It doesn't really do anything for you. So this is why it's very important to pick the right choice of u. This made the problem no easier. It made it maybe look even harder because now you have 2 variables as opposed to 1. So the choice of u is very important. That's step 1. And you may ask, how do you know what u to pick? And notice that whatever u is, you end up dividing by its derivative. So what do I mean? If you let u be, it's going to be some function. right? It was 2x in this case, and it was 1 plus x squared in our other case. Whenever you let u be some function, what do we say? When you take the derivative, you get du is the derivative of this, whatever it is, and then times dx. So remember, the derivative of 2x was just 2 times dx. That's what f prime would be, is just 2 in this case. In the other case, f of x was 1 plus x squared. Its derivative was 2x, and then we tacked on the dx onto that. So that's what f prime would be in that case. And then what happens is, once you do a little bit of algebra, I need to erase that, you just get du over f prime of x is equal to dx. So the dx, the old version dx, is going to get replaced with du over f prime. So this is the guy that needs to be canceling out with stuff. And see, f prime is 2x. That cancels out perfectly with the 2x here when you divide by it. So in the back of your head, you need to think, which one of these choices of u, when I take its derivative and I divide by it, is going to cancel out with stuff. This is the guy that's canceling. So you want to make sure that essentially is the way you want to pick your u. So let's do another example and see. So x squared plus. Okay, so that's what we have. Okay, so now we're going to apply that same way of reasoning to this problem. Okay, so if I let u be this, what's its derivative? Its derivative is 3x squared, right? If you divide by that, is that going to cancel out with the other thing? No, because all of this thing is trapped into cosine. So if you divide by the derivative, this would turn into u. So this is u. Then you divide by 3x squared. It's not really doing much for you, right? Okay, so that's probably not the best choice. So what if instead you let u, now you may say, okay, let u be the cosine of all of this. That is kind of a complicated thing, because if you think about it, if you let u be cosine of x to the fourth plus 2, what's the derivative of this? The derivative of this, you have to use the chain rule to get. It's going to be negative sine of x to the fourth plus 2, so the derivative of the outer function, times then the derivative of the inside, which is 4x cubed. Okay? So then if you divide by all of this, this will be u, right? This will turn into u. So you have x cubed times u divided by negative sine of x to the fourth plus 2 times 4x cubed. Okay, what's good is the x cubes will cancel, right? That's one thing that we have going for us. But now we have u divided by this monstrosity, negative sine of x to the fourth plus 2. And what's really bad is this is now, again, you have a u function and a function with x. That's, again, kind of tricky to deal with. We'll see one example where we can do that. But at this point, you might see what the better choice is just let it be x to the fourth plus 2. That is going to be really nice. So, because that is a thing that canceled out with the x cubed anyways. Okay, so what we're going to do instead is let u be x to the fourth plus 2. Okay, and then when you take the derivative, you get that du is the derivative of this which is 4x cubed times dx. Meaning that du over 4x cubed is dx. Okay, so then this integral transforms into x cubed times cosine of, well, this is u, so we have the cosine of u times what dx is, which is du all over 4x cubed. And that's perfect because now the x cubed cancels and we don't get that weird sign of x to the fourth plus 2 term. So that cancels. And then what are we left with? So, du over 4 is really the same thing as 1/4 times du, right? Because you can think of du as du divided by 1. So this is really just the integral of 1/4 now, cosine of u du. Not too bad. And then remember, what can we do with this 1/4? You can just move it out in front because of the integration rules that we established. So this is just 1/4 integral cosine of u du, which is 1/4, and we talked about what the integral of cosine is. The integral of cosine is sine, so this is 1/4 sine of u plus c. Because a way to double check is take the derivative of this, you should get back 1/4 cosine of u. So what's the derivative of this? Well, this one goes to 0, and what's the derivative of sine? Is cosine. So you get 1/4 cosine of u as you needed. Okay, and then now we want to substitute back. So last step, you substitute back. And we'll get 1/4 sine of x to the fourth plus 2 plus c. And that'll be the final answer. Now I'm looking to see what another good example is, and let's do this one. So x over the square root of 1 minus 4x squared dx. Okay? Now again, if you let u be x, du, so if u is x, then du is dx, and you don't really get anything. That doesn't really tell you much, right? This would just end up being the square root of u over the square root of 1 minus, right? If x is u, then x squared is u squared, right? If you square both sides, u squared is x squared. So 1 minus u squared, and then du. So you essentially get the same problem, 4. You're getting the same problem, just in a different variable, so not much. So you're definitely going to want to be tempted to let u be this more complicated looking thing. And you, again, as we saw, you don't want to include the square root. That's just going to make the derivative really ugly and have more terms that we don't want to deal with. So just let u be the thing on the inside. So then again, du will be the derivative of this, which is negative 8x, and then you times it by dx. Divide du over negative 8x is dx. So then our integral becomes the square root of x all over the square root of u. Don't need to write too much. And then dx is du over negative 8x. Okay? And then just as we needed, you can see that this x here is going to cancel out with that x. And again, you want to think, when I pick a choice of u, I'm going to divide by its derivative. And you know the derivative of this is negative 8x. When you divide by that, you can see it cancels with the x. So then this is the integral of 1 over root u. You get a negative 1/8 out in front because of this guy, du. And then you could rewrite this as negative 1/8, the integral. So the square root of u is u to the 1/2. So 1 over the square root of u is u to the negative 1/2. Because remember, negative powers make you take 1 over the thing in the positive power. So what do I mean by that? I mean, if you have u to a negative power p, that's 1 divided by u to the positive p. So that's why this is u to the negative 1/2. So, and this is u to the negative 1/2 du. And then again, you want to use the power rule here. So this is negative 1/8 times. Now you're going to multiply by 1 over negative 1/2 plus 1, u to the negative 1/2 plus 1, and then plus c. Okay? So let's go up here. So then we have negative 1/8 times, okay, negative 1/2 plus 1 is positive 1/2. So what's 1 divided by 1/2? Well, again, you just flip the fraction, so that's 2. So that's 2 times, and then, again, this is 1/2 times u to the 1/2 plus c, which is negative 1/4 square root of u plus c. And then when you substitute back for u, this becomes negative 1/4 square root of 1 minus 4x squared plus c. Okay. So, with a lot of practice, you'll definitely get the hang of this. You can see it's a very pretty straightforward procedure. Okay. And let me check the time. Now let's look at a hard example of the u substitution. Something that is seemingly, it definitely makes sense, but maybe you don't think about it at first. So let's do this guy. So maybe I should write it like this, so there's no confusion. So x to the 5th times 1 plus x squared. Now you can see that any choice of u, the obvious ones, aren't going to do enough, right? The derivative of this is 5x to the 4th. So if this goes to u, and you divide by 5x to the 4th, that's not going to cancel anything. In the same hand, if you make this x to the 5th again, the derivative of this is 2x, this whole thing here. So if you let this whole thing go to u, and then you divide by 2x, that's going to knock off 1 power to make this x to the 4th, but it doesn't change much. You will have x to the 4th times root u over 2, and that's 2 variables. So, right, when this clears, you have not, and this would be du. It wouldn't really be much easier. But you're kind of on the right track if we kind of write down the details when you do make the second substitution. So let's think about this. Seems like we're stuck, but let's write out the details. Let u be 1 plus x squared. Okay, so then what does this mean? If we do a little bit of algebra, we see that u minus 1 is the same thing as x squared. And so if you square both sides, that means u minus 1 squared is x to the 4th. Okay, so this is one important thing that we see here. Okay. And because of that, we're going to rewrite this guy in a very suggestive way. We're going to write this as x times x to the 4th, right? That's what x to the 5th is, times this guy. Okay? So we can see now that we've written x to the 4th in terms of u's and stuff, which is good, so that when we make the substitution, this x to the 4th will become something with a u in it, so we don't have this two variable business. Now you may ask, what about this trailing x here, okay? The trailing x is, if we work this out, if you go here and take the derivative, this means that du is derivative of this, which is 2x dx. And then if you divide, so du over 2, so instead of dividing by the whole thing, we're just going to divide by 2. We see that du divided by 2 is x dx. That's pretty sweet. So this x times dx here, that whole thing is going to get replaced by du over 2. And so now we can replace, there will be no more x's. So let's see what happens when we work all this out. This is very, very clever. You have to really sit there and think about it. So this x times dx will really get replaced with the du over 2. And I'm going to write it this way just to maybe rattle your brains a little bit for a second. So du over 2, and then x to the 4th we said is u minus 1 squared. And then this guy we just said is u, right? So times root u. Okay, then maybe like, hey, all this stuff is to the right of du. We normally write du all the way at the end. And again, as an analogy with the Riemann sums, the du is the old delta x. So you can think of it as just a number, right? It's getting multiplied. And the order you write things doesn't matter. So I can say du times this, or I can say all this times du. It doesn't matter. You can put it at the beginning or the end, or in the middle. It's just going to look weird in the middle, but some people prefer to write it here. So it's good to see this, okay? Now, I like putting it at the end, so I'll go back to that now. Okay, and then what we're going to do is we'll expand this. U minus 1 squared, remember? It's just u minus 1 times u minus 1, right? And this is u squared, u times u is u times negative 1 is minus u, negative 1 times u is minus u, then negative 1 times negative 1 is plus 1. And then when you combine this, negative u minus u, you get u squared minus 2u plus 1. Okay, so we're going to let this u minus 1 squared be this guy. So we have the integral, and if we want to separate the du and the 2, this is like 1/2 times du, right? So we'll just pull out the 1/2. So we'll have 1/2 out here. And then this guy is being replaced with that. And again, because it's not a single number, it's not a single expression, just like you have to put parentheses around all of it. And that whole thing is times, now I'm going to write this as u to the 1/2, the square root of u, du. Okay? And now I can distribute this to each piece. So u to the 1/2 times u squared is u to the 2 plus 1/2, right? You just add the powers, and then minus 2, and then u is like u to the first power, right? U is like u to the first. So this becomes u to the 1 plus 1/2, and then plus, well, 1 times anything is itself. Okay, and then now we have 1/2 integral of 2 plus 1/2 is 5/2. Once you get a common denominator, so u to the 5/2 minus 2u to the 3/2 when you add this. Okay? And again, now you can split all of these integrals up if you want to, or you can just do all of this in one go. You can just apply the power rule multiple times. So I'll come here when I'm done down here. So you'll get 1/2. 1/2 will multiply all of this stuff. So 1/2 times the integral of all of this this will be repeated applications of the power rule. It'll be 1 over 5/2 plus 1, u to the 5/2 plus 1, minus, and then 2. So this 2 here, remember, if we split this into 3 integrals, you can see the 2 would just come out in front of the integral, right? This would be the integral of negative 2 u to the 3/2, and then you'd pull the minus 2 out. So the minus 2 is going to multiply whatever the integral of this is, which is the 1 over 3/2 plus 1, 3/2 plus 1. So negative 2 is multiplying all of that. So you have negative 2 times this guy, and then this one is 1 over 1/2 plus 1 plus c. Okay. And you might say, why aren't you distributing the 1/2 to the c? Again, c is just any real number, so 1/2 times c can just be any number. Like had c been 2 and you multiply it by 1/2, you get 1. But if you want it to stay 2, you just let c be 4. And then 4 times 1/2 is 2. So if you desire, you can still make this any real number. So just let it be c. Okay, and then we'll come up here. So this is 1/2 times, so 5/2 plus 1 is 7/2. So 1 over 7/2 is 2/7. So this is 2/7 u to the 7/2 minus, okay, now we have minus 2 times 1 over 5/2. Well, if you flip this, 1 over 5/2 is 2/5. Okay, so then negative 2 times 2/5 is negative 4/5. So minus 4/5 u to the 5/2. And then plus, this is 3/2, so when you flip it, it's 2/3. 2/3. Plus c, and then, okay, so now you can start distributing the 1/2. So 1/2 times this is 1/7, and then let's substitute back for u at this point too. U is 1 plus x squared. So so 1 plus x squared to the 7/2, and then 1/2 times this is this 2 will cancel with the 4 to give you 2/5, and then 1 plus x squared to the 5/2, and then 1/2 times this, the 2 cancels, so plus 1/3, and then plus b. So this is the final answer. It's quite amazing that you can get this answer. So we did all that work, but we got a good answer. All right. Okay, so then the next topic is how do you do this with a definite integral? So if you do substitution, how does this work with a definite integral? What changes? And the easiest way to explain this is to just do an example, essentially. So let's go back. So let's do this guy here. Okay. So we don't have the other thing out in front. We just have this. Okay, so there's almost, there's literally no other choice for you, right? Except for what's inside the square root. So you're going to let u be 1 plus x squared. Okay? Meaning that du is derivative of this 2x dx, and then du over 2x is dx. Oh, sorry, this is a 2x. I was going to say this is not going to work out. Okay, let's redo this, sorry. So this is du. Derivative of this is just 2, right? This derivative is 0. This derivative is 2. Okay, so then du over 2 is dx. So this is the integral from, and I'm going to refrain from writing numbers here for a second. So this is u, so this is root u, and then dx is du over 2. So this is a good substitution. We can actually, take this integral. But what should you let these limits of integration be? Well, the idea is if you let u be this, you can figure out what u should be at x is 0 and at x is 4 by just plugging in. So u of 0, whenever x is 0, what is u? So when x is 0, what is u? It's 1 plus 2 times 0, which is just 1. So this is going to get replaced with 1. And then what is u when x is 4? Well, right, you can think of u as a function of x, right? Maybe I should write this explicitly. U as a function of x, because u explicitly depends on x. Well, if you give me a value of x, you can get u. So then u of 4 is, stick 4 in here, you get 1 plus 2 times 4, so 1 plus 8, so 9. So this is 9 now. Okay. And you're good to go at this point, because now you can do this integral super easy, or easier than the previous example. So this 2 again, remember, it comes out as a 1/2. And then you can rewrite this as u to the 1/2, right? So maybe I don't even need this. So the 1/2 comes out in front, and then what's the integral? Or maybe I should do this just to be extra safe. I'll write this in red again just to be as a reminder. Okay, so then we've seen this so many times now, the integral of u to the 1/2 or the square root of u. So this is 1/2 and then, you know, it's 1 over 1/2 plus 1, u to the 1/2 plus 1. Evaluated now, because it's a definite integral from 1 to 9. So this is 1/2 times 1 over 3/2 u to the 3/2 evaluated from 1 to 9, which 1 over 3/2 is 2/3, right? So this is 2/3, and then 1/2 times 2/3 is just 1/3. So these cancel, and you just get 1/3. Okay, and then this is super easy. At this point is 1/3, 9 to the 3/2 minus 1/3, 1 to the 3/2. I shouldn't use the word easy, I should say straightforward, because, you know, anything in life can be easy or hard depending on if you've just been doing it for like a few days versus years. So sorry for using that word. Easy is not a good word. It's more straightforward. It doesn't require as much thinking and processing. You're kind of just using the definition. Okay, sorry about that. And again, you could yell at me in real life, but this time you can't. So I gotta yell at myself. So whenever the dust clears, right? So what is 3/2? How do you find something to the 3/2? Remember, this means take the square root of this number and then cube it. So this is 1/3 square root of 9 cubed minus 1/3 square root of 1 cubed. And so this is 1/3. Okay, this is 3. So when you cube 3, you get 27. And then, you know, this is just 1, right? Square root of 1 is 1, cube it, you get this. So minus 1/3. And then, you know, 27. So let's just write this as 27 over 3 minus 1 over 3. So this is 26 over 3. Final answer. And again, it's better to not simplify this. Had you just said, oh, well, 27 over 3 is 9, then you would have to you'd have to turn this into a fraction again. And so it's better to not simplify in this case. Now, one last thing to mention is, if you back substitute at this stage, so there's two ways to do this essentially is what I'm saying. If you substitute back at this stage and make this 1/3 instead of u to the 3/2, 1 plus 2x to the 3/2, then your limits of integration should not be 1 to 9. They should be the original limits of integration. So that's your choice. Is essentially you can do this either way. If you keep it in this form, then you can use 1 to 9, the new limits of integration, because that corresponds to u. But if you switch back to a variable of x, then you have to use the old limits of integration, which were 0 to 4. And this should work out to give you the same answer. So you can double check this, and it's just kind of preference, really. It's up to you. But okay, so we talked a lot about u substitution. We'll finish that up next time and move on to some other stuff. Okay? See you guys later.